is also termed as polyphase circuits. Already we have discussed single phase circuits, in which we have discussed that whenever a coil is placed in a magnetic field, EMF is induced, and that EMF induced is used to supply a load, and the power consumed by a single phase circuit is VI cos of phi. Now, in place of single phase circuit, we are discussing three phase circuit. Obviously, it has certain advantages of single phase circuit. Advantages. First advantage, cost of three phase system is low. Whether it is a machines, transformers. In machines you have motors, transformers, transmission line, etc. For example, your electrical energy is transmitted from generating station to substation to distribution station to end users. And this generating station may be thousands of kilometers away from the end users. Now, if you generate with single phase, you require two wires to supply the load. If in place of three phase system, we require three wires in place of two, system becomes three phase. Power transfer capability becomes 3 times. With increase in one wire, increases the transformation capability by 3 times. But obviously, the cost will be low. Likewise, in your machines, for example, in motor, outer body is same, core is required same, with certain enhancement. The cost would be obviously same. Bearing required same, shaft required same, hence the cost would be low. In transformer, the size of the core is not too expanded in comparison to single phase. It means the cost of devices is same. That's why in our industrial applications, most of the applications are of three phase system. Whereas in case of domestic applications, we use it single phase. These are the exceptions. Another advantage is the cost is the major factor, performance. Performance of three phase machines are better in comparison to the single phase machines. For example, in case of a transformer, losses would be lesser for the same rating because the core material required to be added to be lesser. Correspondingly, efficiency would be better. For example, in case of rectification, the output is smooth. In single phase system, rectification is this one. And in three phase system, we will get somewhat like this one. So this output will become smoother. That's why we prefer three phase system over single phase system. But obviously, when we are telling the size of the machine would be lesser, material required would be lesser for the same rating. Means the size of the machines would be also same for same rating. Would be also lesser for the same rating. That's why we preferred three-phase system in comparison to single-phase system. And that's why this three-phase system is in existence for generation, transmission and distribution purpose. How three-phase EMF is generated? Generation of three-phase EMF. But obviously, the EMF being generated by the generators. And in case of three-phase system, we will have three coils in place of single coil. In single phase we use a single coil, in three phase system we use three coils. And whenever an coil is being rotated in a magnetic field or magnetic field linking to that coil is changed, EMF will induce in the coil. Hence, your current will flow through the coil if load is connected. In place of single coil, we will have three coils. Let first coil be denoted by A dash. In three-phase system, all the three coils would be displaced by an angle of 120 degree electrical. Let another coil B dash. Another coil C, further C dash are displaced each other by angle of 120. So all these coils are displaced each other by an angle of 120 degree. And whenever, for example, we see the magnetic field, and this magnetic field is rotated across a stationary coil, EMF will increase in the coil. As the coils are displaced each other by an angle of 120 degree, hence their EMF will be induced by displaced by an angle of 120 degree. In single phase system, we discussed that EMF induced by EM sine of omega t. For example, in first coil, EMF induced is given by EA. Then second coil, all the coils are displaced at an angle of 120 degree electrical. Hence, their EMF induced would be displaced by an angle of 120 degree. That will be EM sine of omega t minus 120. EC would be EM sine of omega t minus 240. Now, you will observe that all the coils are displaced each other by an angle of 120 degree. Their EMF induced will also be displaced by an angle of 120 degree. These coils may be represented by A dash starting at finish end, B dash starting at finish end, C dash starting at finish end. If you observe, the angle is between all these three coils is 120 degree. These coils may be represented in place of A dash, 1 dash, 2 dash, 3 dash. Or in our electrical engineering, we generally define these three phases in terms of R, Y, B. That is R dash, Y dash, B dash. You can represent it by any way. And if we draw the wave diagram for this generation, you will observe that this will be like this. Let first, for better representation, divide these coils 90 degree, 270 degree, further divided into two halves. You can easily represent by better way. So this will be 30, 60, 120, 150, 210, 240, 300, 330 and this is for the line for the maximum value. That in first coil EMF induced is given by this one. So this is the wave shape. We have also studied in our earlier lecture. Second phase, let it be represented by A. It's lagging by an angle of 120 degree. B phase. Third phase is further displaced by an angle of 120 degree. 240. And you will observe that at any instant the net EMF would be 0. 0 equal and opposite. Maximum, negative maximum. And which all the three phases are displaced by an angle of 120. Their maximum value will be displaced by an angle of 120 degree. Their 0 points will be displaced each other by an angle of 120 degree, and their negative maximum values are also displaced by an angle of 120 degree. And the normal phase sequence is another term generally used, phase sequence. A, B, C or R, Y, B. If we change it, the phase sequence, we can change it just simply by reversing the direction of rotation, or if we reverse the direction of rotation, the C coil, the polarity would be changed. It may be CB A or CYB. So generally we indicate in them RYB phase sequence or BYR, or means what we have changed. If we interchange any of the two phases, any of the two coils, if we interchange, but obviously their sequence would also be changed. We can draw the phasor diagram also. We have also discussed earlier that phasor diagram is just representation of each phase by a line. Representation of your alternating quantity by a line. For example, E, voltage of phase A. Yes. Displayed by an angle of EB, EC. All these phases are displaced by an angle of 120. So this is the phasor diagram for three-phase system or three-phase EMF. All these three phases are displaced by an angle of 120. Correspondingly, if load is connected, their phase currents would also be displaced by an angle of 120 degrees. If we want to see the resultant of any two phase each, what will be the voltage? You can simply draw the voltage between any two phase each and you can get the resultant. So we will discuss in preceding section about this resultant voltage. Important is we have three coils in three-phase system. But obviously we will have three loads. Interconnection of three phase. These three phase each or these three phase load may be connected either in star or delta. Star or also known as Y. Delta. So we will understand what will be the relationship between the line voltage and phase voltage when the system is connected in star, line current, phase current, and what would be the power with the help of the phasor diagrams. Your phasor diagram just indicate the relationship between your voltage and current of a particular phase. So we will draw the phasor diagram. So here we have three coils and three loads, load L1, L2, L3. So first we will discuss star connection. In star connection, we have, for example, start and finish end. Start and finish end. Start, finish end. The star connections you have already discussed, but you are aware about that. In star connection, starting end or finish end of each coil is connected to one common point. And this one is the another point. If we connect these 3 points at a common point, it will form a single connection. Either starting or finish is connected to one common point, and these terminals may be defined as R, Y, B, or they will be R, Y, B, and this point is neutral. The current supplied, let EMF induced in this coil be denoted by ER, EY, and EB. Correspondingly, current would be IR, IY, IB, where this can be denoted by EA, EB, EC. Whatever you want to, you can denote it. So now here we have considered R, Y, B. This ER is the EMF induced by this coil. This one. EY be the EMF induced by this coil. And EB be the EMF induced by this coil. And their return path would be from this load would be connected like that. It would be IR plus IY plus IB. For example, if the current here is IR, IY, IB. Return path is same, and this would be IR, IY and IB. And this should be resultant current in the neutral should be 0. IR plus IY plus IB, if the system is balanced, it would be 0. As we have this seen the wave shape, and we observe that at a particular point, this is the wave shape for current, at a particular point the net current is 0. If we get the algebraic sum, it is 0. So it should be 0. If the system is balanced and current in all the branches are same, so it would be 0. One is 0, another has negative value, another has positive value. These will cancel each other, and at a particular point it would be 0. Here maximum both currents A, R, Y, B. Y and B are negative values, and that negative value will be equivalent to this. For example, this is 10 ampere, this would be minus 5, minus 5. The net current would be 0. That's why this IR, IY and IB will be 0. And this neutral can be represented by a line. Now, here these are the phase voltages, and voltage between two lines. This is line 1, line 2 and line 3. Would be equal to the line voltage. Here the voltage is VRY, and we can remove this also. VYB and VBR. These voltages between the lines is known as line voltage, and voltage of each phase is known as phase voltage. This may be represented by VER, or that may be represented by VR. So means your ER, EY and EB are phase voltages, and if the system is balanced, so we can represent it by E phase or V phase. Likewise, your VRY, VYB and VBR are line voltages. So let us draw the phasor diagram for the star connected connections. Voltages and currents in a three-phase system, let us draw the phasor diagram. All these voltages ER, EY and EB are displaced each other by an angle of 120 degree. There, let us, the load is inductive. This is a simple representation by a line. If the load is inductive, their corresponding current, phase currents IR, IY, IB would be displaced by a certain angle, let it be phi. EY and IY lacks the applied voltage or generated EMF by angle phi. So means if the voltages, phase voltages are displaced by an angle of 120 degree, their corresponding phase currents would also differ by 120. So here ER, EY and EB are the phase voltages, IR, IY and IB are the phase current. Let us discuss the relationship between these line voltages and phase voltages in this case of star connection. First thing we will discuss line voltage and phase voltage. Phase voltage. So their line voltage are the VRY, YB and VB are the line voltage. Are the line voltages and may be denoted by, if the system is balanced, may be represented by VL. They will be same and they will be equal. VR will be equal to VYB and VBR. If ER, EY, EB are same and they may be represented by E phase or V phase. That is your phase voltage. We have to observe the relationship between line voltage and phase voltage in case of star connection. VRY is the voltage between this. So here they are in opposite direction, looks opposite direction. So their voltage would be the phasor difference. So how will you represent it between R and Y? We just phasor difference, extend this phasor in opposite direction. So this will be represented by EY. This EY after a phase displacement or in phase opposition, it is represented by EY. We just extended it in opposite direction. And VRY be the, draw the parallelogram. We just draw the parallelogram and VR by the field, and this VR by is ER minus EY, phase difference. Or phasor difference or vector difference. So we can find out the VR by simply what will be this angle? If this angle is 120, this is in phasor position, so this will be 60 degree. But obvious, if both ER, we have discussed that in a balanced system, your ER or EY and EB are equal. Hence, the angle would be 60 degree, or this would be the half of the angle, it would be the 30 degree. Leave it. What will be the VR? We can simply find out either by using parallelogram method or by using method of component. Let us use the method of component. What is this angle? 30 degree. Sum of, at this angle, sum of horizontal components x. VRY is the sum x square plus y square under the root, where x is the sum of horizontal components, y is the sum of vertical components. So what are the sum of horizontal? Let it be ER cos 0. ER cos of 0. EY makes an angle 60 degree with this ER. It will be EY cos of 60 on horizontal component scale. ER sine of 0 on vertical components, its value would be plus EY sine of 60 degree under the root. Or ER cos 0, ER plus EY cos of 60 degree, sin 0, 0, EY sin of 60 degree. As we know that your ER is equal to EY is equal to EB. These are the phase voltages, and that is equal to E phase. Then put this value here, E phase plus E phase cos of 60 plus E phase sine of 60 degree square, or this would be equal to, you can take this outside, 1 plus cos 60 degrees square plus sine square 60 degree, or further simplify it, E phase 1 plus, yes, cos square 60 plus 2 cos of 60 plus sine square 60 degree, or this would be equal to E phase sine theta, sine square theta plus cos square theta 1, so this will be 2 plus 2 cos of 60 degree, or this can be written as E phase 2 1 plus cos of 2, let us divide and multiply by 2. We know cos of 2 theta is 2 cos square theta minus 1. So this will be 1 plus cos 2 theta is 2 cos square theta. So this can be written as 1 plus cos 2 theta E phase 2 into 2 cos square 60 by 2, or this may be written as 2 cos of 60 by 2 E phase, 2 E phase, 2 E phase cos of 60 by 2, and cos 30 or 2 of cos of 30, and value of cos 30 is root 3 by 2. So VRY will be 2 E phase root 3 by 2. So VRY is, that is equal to root 3 E phase. This is important one. VRY is root 3 E phase, or then this may be represented by, or we can write it as root 3 of V phase. So in case of star connection, your line voltage would be equal to root 3 of V phase. In your household, you get 3-phase supply as well as single phase supply. Single phase supply is between phase and neutral. This is your transformer connection. It has 3 coils and you get 4 wires. Some consumers may have this one phase and neutral. Some get all the 3 phases and neutral. Between phase you get phase voltage. Between line you have line voltage. If you measure the voltage between 2 lines, you observe that the voltage is 400 volt, whereas your household appliances requires the voltage between the 200 to 250 volt. Now if you get the root 3 of it, you will get, it will be around 230 volt. Means if you have 3 phase, your voltage is 400. If you have single phase equipments, that is for your lamp, fans, mixie, fridge and other appliances, your requirement is 230 volt for single phase appliances. So you get both the voltages 400, as well as if you connect between 2 lines, you will get 400 volt. If you connect between phase and neutral, you will get 230 volt. Now similarly, V by V, line voltage between Y and H, E by minus EB. E by EB. Extend this. EB. Then draw the parallelogram. this will be the V by B, and this angle is 60 degree. You will observe that if you repeat same process, same calculations, you will get V by B is root 3 of B phase. Likewise, between phase B and R, extend this in opposite direction, minus ER, draw the parallelogram. VBR, this angle is 30 and this whole is 60. VBR is EB minus ER, phase difference, phasor difference. And this will be RH root 3 of V phase. As their phase voltages were equal, we have observed that their line voltages are also equal. VRY is equal to V by B is equal to VBR is equal to, or that may be termed as VL, line voltage. Voltage between two phases, voltage between two lines is your line voltage. Therefore, your VL would be root 3 of V phase. So this is the relationship between phase voltage and line voltage. Now you will observe that your line voltage would also have the phase difference of 120. And these line voltages differs the phase angle with phase currents by the angle of 30 plus 5. All the line voltages and phase voltage difference is 30 degree. Line voltage and phase current difference is 30 plus 5. 30 plus 5. 30 plus 5. 30 plus 5. 5. So this is the difference between line voltages and phase voltages. Now, line current and phase current. We have these three phase currents. These are three lines: IR, IY, IB. We have already done the diagram. This coil is connected in series with the line. Whatever be the current in each phase will be the current in the line. In first line, line 1, line 2, let it be current be I1, let in line 2 current be I2, and line 3 current be I3. As these coils are in series with the line, their current will be same. Your I1 will be equal to IR, I2 would be equal to IR, IY. and I3 would be equal to IB, where I1, I2 and I3 are the line current. As your load is balanced, these currents would also be equal. So this I1 would be equal to I2 equal to I3, and that will be equal to the line current. As load is balanced, there IR, IY, and IR is equal to IY is equal to IB, or is equal to I phase. That is your phase current. Therefore, IL is equal to I phase. So in star connection, your line current would be equal to the phase current. Third one is power. Third point in this, we have to observe power. Power in a three-phase star electric system. Power consumed by a three-phase load. What is power in single-phase system? We have discussed power is VI cos of phi. We have already discussed ER is the phase voltage, IR is the phase current, phi is the phase angle between these. So in three-phase system, what would be the active power? Power which is actually consumed in the circuit is given by P ER IR cos of phi plus EY IY cos of phi plus EB IB cos of phi, where AR, IR are the phase voltages and currents. Phi is the phase angle or angle between this phase voltage and phase current. As this ER, EY and EB is phase voltage, IR, IY and IB are phase current. For a balanced system, then active power will be V phase I phase cos of phi plus V phase I phase cos of phi plus V phase I phase cos of phi. Means 3 times of the single phase system. 3 coils, it will be 3 times. Where phi is the angle between this phase voltage and phase current. We know in case of star connection, V phase is VR by root 3, I phase is IL cos of phi. So your power would be root 3 VL IL cos of phi. So in 3-phase system, power is root 3 VL IL cos of phi. One thing is important. What is this phi? This phi is the angle between phase voltage and phase current, not line voltage and line current. Because here current would be same. What would be the phase angle between line voltage and line current? It would be 30 plus phi. Because IR is equal to IL. So this phi is the angle between phase voltage and phase current, not line voltage and line current. And in three-phase system, if you mention root 3 VI cos of phi, it means this V is the line voltage, I is the line current. And if in a problem it is written that is a 400 volt or 200 volt 50 hertz system draws a current of 10 ampere, it means this is the line voltage, 10 ampere is the line current, and if the angle mentioned is, it means the angle between the phase voltage and phase current. If the voltage given is the phase voltage, he will mention that the phase voltage is 200 volt, phase current is 10 ampere. Like in single phase system we discussed that if voltage is given at 200 volt, it means it is RMS value. Otherwise, that will be, if average value is given, then he will mention that this is the average value, this is the maximum value. Likewise here, this is the line voltage and line current. And phi is the angle between phase voltage and phase current. Reactive power in three-phase system is given by root 3 VL IL sine of phi. Likewise, your reactive power in case of single phase system was given by VI sine of phi. And reactive power that will be denoted by Q. Or your apparent power will be denoted by S. That was active power square, reactive power square under the root. Or active power we have find out VL IL cos of phi, reactive power root 3 VL plus 3VL IL root 3 VL IL sine of phi, or it will be root 3 VL IL cos square phi sin square phi, root 3 VL IL. This is your apparent power. Because in three-phase system, single-phase system, apparent power was given by V into I. In three-phase system, apparent power is 3 V phase I phase. In terms of line, it would be root 3 VL I.